I am Stephane Callet. It's a pleasure to join Smart Transit this year again, and to share with you some experience on the project in Paris. I work for the SNCF major train operator in France, and we are introducing the CBTC technology in the Paris area. The presentation will be about the first trial running trains were intended to validate some key technical functions like train localization, train positioning system, and the radio link between the train and onboard. But first of all, a few words about the EOL line extension project. The EOL line is an E-line, also called, is a west-eastbound in Paris. It's a 20 years old line, inaugurated in the year 1999, and then a few years after, in the mid of the 2010 years, for instance, we plan to extend the line on the westbound, about 55 kilometer line extension, in order to address the increasing demand on transportation from east side to the west side to Paris and vice versa. Nowadays, the line is operated with 350,000 passengers a day, and we know that by the opening of the westbound, we will probably have the first day around 600 to 700,000 passengers a day. We have an east-westbound in Paris. The red line, the airline, is already over 1 million passengers a day. So there is today already, let's say before the COVID, but today it starts again. We need to relieve this red line, this A line, by an additional east-westbound based on the CBTC technology. Today we have the KVB, the ATP legacy system in France, which allows us to operate at 300, 400,000 passengers a day, but not at 6 or 7 or 800,000 passengers a day. So it looks like that. Today the project is also a rolling stock project. We have bought some new trains, 71 new trains for the EOL line, and in total the contract is awarded for 255 trains from Alstom Bombardier. We call them the RNG, new generation of train, double-deck trains, and beside this, we have an infrastructures project, the 55 kilometers extension on the westbound, with new stations, with 8 kilometers new tunnel underground in Paris area, from the business district La Défense to the main station Paris-Saint-Lazare. Haussmann Saint-Lazare, precisely said, is the limit or the edge of the existing east line, E-line, and the new line to the westbound. We'll introduce a new rail traffic management system. We call it NextEO combined with ATS. We call it ATS Plus on this project. It looks like that. We will have operation with the legacy system on the eastbound and on the westbound. We call them KVB. And in the middle of Paris, around 15-20 kilometers of track, of line, let's say, we have the NextEO CBTC system, mostly intended for performance enhancement, because we have a kind of overlay of operation. The train of the eastbound turns back at the edge of the NextEO westbound domain and goes back to the eastbound, and vice versa. The train coming from the west will turn back and at the edge, at the frontier between NextEO and the east domain, and will drive back to the westbound. So there's an overlay of the two train traffics from the east and the westbound in the middle of Paris, and this is why we need to enhance the performance using CBTC moving block. Of course, moving block in the CBTC is based on the pyramid ATP, ATO, ATS. We will implement all three systems together, starting first with the ATS for train operation and train regulation, traffic management of the line with the conventional system, and then add ATP and ATO together in the second step in the year 2023. The challenge is to introduce this in the existing system, because we have the westbound will be the new line extension with computer-based interlocking and so on. But the existing part of the line is already fitted with relay-based interlocking, with different kind of generations of relay-based interlocking. And it's a major part of the track, because it's also operating all the traffic from the eastern part of Paris, going from Paris to Germany, to the rest of the eastern part of France, which will also be operated on this domain. So part of the domain will be CBTC, part of the domain will be conventional ATS operation. This is the driver's cabin, let's say the simulator. Today we can implement the software and the look and feel, the MMI of the driver in this kind of simulator. It looks like an ERTMS environment, but it's very similar to many CBTC environment, with a DMI, an MMI for the driver, with movement authority, or let's say target speed and some other indications about speed restriction, walk zone, and so on. As usual on this kind of project, little interaction, but a few interactions with the train operator for acknowledging, for instance, on the west part of on the left part of the slide, acknowledging transition between legacy system and CBTC systems. Train will be operating in ATO mode. Automatically will switch from manual driving to ATO mode, and vice versa, with the acknowledgement of the train driver to keep control on the train. This is one of the major technical improvement on CBTC for this project. This is a dynamic handover of trains from different domains, and the second particularity and technical particularity is the interoperability with ERTMS at the frontier of the system. So back to the kernel of this presentation. All these systems, CBTC-based systems, are based on two major functions that must be properly addressed: the train position system, train localization, and the radio link between train and wayside. Why should we test them in this project at a very early stage? We do not have the trains, we do not have the complete system already designed and the software finished. We have most of it today, but last year in 2019 it was not the case. But we decided to address the risk of these two functions, these two technical functions. Let's say if the CBTC radio link does not work properly, then there's no CBTC at all, and if the train positioning system does not work properly as well, there's no CBTC on this project available. Whatever the different functions we will put on it, speed control, ATO, and so on. So we decided to validate them, because we said there is a major difference between the conventional CBTC environment for urban traffic, like our colleagues from RATP or the other operator for metro lines. We have high-speed operation. We do not operate train with 60 or 80 kilometers per hour. We operate at 120 and even sometimes more kilometer per hour speed. We operate in tunnel and in open sections with overhead lines, but also with a lot of devices on the track, on the sleepers, for instance. We have the CCTV cables, and the balise will have to be installed underneath under this cable. So we assumed that probably the precision of reading of the balise will be alterated and will be degraded due to these cables. And we said CBTC relies on the high accuracy and precision of balise reading, allowing the train to precisely stop at station, for instance, at platform. So we wanted to check all this, starting with the radio. During this radio trial, we had a configuration very close to the target configuration regarding the speed, the maximum speed, regarding the layout of access points with the distance between access points and the layout of antenna linked to these access points on wayside, regarding also the overhead lines and the power on them, regarding also the rolling stock, the double-deck rolling stock. So we decided to take a train very close to that, and also to take to choose a portion of track very close to the conditions we wanted to address, especially the speed and the maximum speed, and with some bridges and some other constraints interesting to test also. So we had a portion of track of several kilometers with a few access points and a few antennas on track, with a double coverage of the track, exactly as we have in the studies of radio layout from the manufacturer for the layout on the line, in the tunnel, and on the outside the tunnel. The results were very profitable to analyze. We have a large amount of train running, with a large amount of message exchanges, with a nominal situation and some degraded situation. We provoked some degraded situation with switching off some, for instance, some access points, 1 out of 2 access points, and so on. The results were interesting because first of all, the radio coverage, the effective radio coverage, is very close and very consistent with the theoretical one. And this is for us very important because the manufacturer had a design on a theoretical basis, and modelization of the line and of the tunnel and of the track, and the distance between the access points and the orientation of the antennas and so on have been fixed only theoretically. And we are currently implementing the fiber optic and the power supply for these future access points and antenna that will come in the second step. So if we have to change something, it will be too difficult and very costly to adapt the layout. So it is lowering the risk of future changes in the layout by having these results. The handover also was very smooth between these access points, even also integrated situations with one access points out of order, which should be also the behavior on the line when there is a problem. And regarding the performance, the performance is one of the key issue with CBTC. For the performance level we want to achieve, there is also an allocation to the radio link, which is something around 100 milliseconds, and we wanted to check if we achieve this kind of performance. So the measurements allowed us to have a total latency time from wayside to onboard and vice versa, and we had for these latencies in 80% of the cases less than 100 millisecond latency time. And there was no Doppler effect on this on the signal. We assume at this speed, of course, with this kind of technology, the Doppler effect should be not very significant, and it was proved by the measurements. So this conclusion allowed us to be confident for the next steps, deployment, installation, and oncoming testing in the next years, in the next 2 years, regarding the radio. So I propose to move to the second topic and the second key functions we want to check. This is the CBTC train positioning with the new system of balise. What is very different from the existing solutions already proven by our manufacturer is that we do not use the conventional DigiSafe balise our manufacturer Siemens use usually for this kind of CBTC system, but we enforced the use of Eurobalise because of maintenance constraints, but also because of interoperability concern and of transition concern. So there was a choice, a technical choice that must be validated by this demo, by this mock-up. So we implemented also in this case we wanted also to address the issue of the train speed as well. Same for the radio. This is different, very different from the train speed in tunnel with metro lines. Again, the double with conventional metro in Paris. So what about the accuracy of that? What about the robustness of reading all these balises? We were also quite confident on this case. On this, because we have the Eurobalise used in high-speed lines on the SNCF line, but not used with the technology of the manufacturer combining CBTC DigiSafe technology and ERTMS balise reading technology. Different also conditions of rolling stock, double deck rolling stock with a different height of balise antenna position regarding the balise on the wayside. So we implemented, of course, the complete onboard unit, or at least the necessary part of the onboard unit, with the different sensors for speed and for balise reading on the wheel set. And here's the timeline of this sub project. Let's say it lasts something like 1 year, from equipping the fittings of the train and the wayside with the studies associated to that, and gathering some thousands of running of balise reading within a few months. Half of a year of monitoring of the train positioning system. That means a few thousands of balise reading. Here on the left of the slide, you can see typically a Eurobalise with the CCTV for the train driver and platform communication video link. That was also one of our concern about what kind of precision in balise reading do we have when having this kind of balise layout and proximity to the CCTV antenna. There were different kind of configuration of layout to address. Typically, in this kind of system, we are very sensitive to the speed. We are sensitive also to the other system, the mass, the metallic mass, the KVB, the other balise close to this. We are sensitive to curves, of course. Balise reading in curves can be an issue, and we are sensitive also on the track bed and the kind of sleepers. We have 17 types of different sleepers on the CBTC domain on the E-line, due to historical reasons of the different phase of the line and the different manufacturers and the different maintenance operation between in the last 30 years. So in this case, we have different environment, wood, concrete, sleepers, and so on. So we address all these kind of configuration on the line to have a real representative set of configurations. I will not detail the different runs, but this is typically the kind of runs we had for conducting the trial running. At night, mostly when we were trying to make some specific measurements in order to have specific speed, high speed, for instance. But during the day also we have conventional runs, and the train were operated with passengers, and in this case the train was monitoring and gathering the balise reading, and we could just take the log once a week, for instance, to pick up the necessary information and interesting in statistics from the onboard computer unit of the train. Here's typically one measurements that we extracted. This is how we are sensitive from the antenna H distance to the balise reader to the balise on the track. We have here two channels: the orange channel and the blue channel, and with the different dots are the different balise with different position on the track compared to the antenna. And we can see that we are, of course, very sensitive to regarding the power, let's say, of the level message reading and balise reading from the antenna. We are very sensitive to the position, to the distance from the train antenna and the wayside balise, of course. So depending on the train and the erosion of the wheel, of course, during the months and the years, the train antenna position will change, and all the trains are not completely similar, of course. So we have to be robust to different to a wide range of distance, and we have assessed that in fact we are very close to the theoretical results, even much more better than what we thought. And we are really above the threshold we have in the target. More interesting is the accuracy. This is typically the results we obtained. We should have, regarding the main lobe, we have an extension of 60 centimeters that allows us to have a very accurate train position with estimating the middle of the lobe. We have the precision and the accuracy of the train when running on the balise, and recalibrating the position of the train. And the theoretical labor measurement was 64 centimeters for the lobe, and regarding a given level of 44 dBm. And for this kind of measurements, with several thousand of balise reading, we got a stable range of 60 centimeters plus minus 1 centimeter. So something very clean and with robustness of balise reading. Both criteria have been mostly and with highest priority observed and monitored during this trial running. So thank you, and this is the last slide, just to show where we are on the project. The trial running on a V-cycle. We're at a very early stage in 2019 during the design phase. We have ended the design phase on this project. We are just ongoing with installation, and we have some test and validation, mostly on the manufacturer side, and some started on the operator's side at the SNCF. And of course, we will have on-site testing in 1 or 2 years with the full system configuration, and we'll be very happy to rely on these two corner functions. And hopefully, we expect that there will be no surprise, at least on these two functions. Thank you very much for your attention, and enjoy the Congress as well.